was asked just to give a brief history, so that's what I'm going to do. You've already heard some engineering details. So this presentation is light on that. Carolina was kind enough to share her slides. She, like me, worked on them until late yesterday. So I simply want to recall to everyone what are the elements of a recording system and why NeuroPixels are unique. All of these elements are in every recording system. You need sites. You need an amplifier for every site. You need a multiplexer if you want to not have as many wires off the mouse as you did on the wall, which was the case when I joined the field 15 years ago, and an A to D converter, and then some way to get your data to the computer. The unique thing about NeuroPixels is that all of these are on a single integrated circuit. Yeah. And so before we had NeuroPixels, we were doing this in 2010 when I first traveled to IMEC and tried to find a path to make a high channel count probe. By far, the dominant technology was twisted wire tetrodes. The alternative technology were silicon probes. They are in fact much older. Kensal Wise, who was at the University of Michigan, first published on this in 1970. The problem is that you couldn't get enough channels on a shank. And so this is a typical shank of a Buzaki 32. You notice that the density is okay, but you only get 150 microns of tissue coverage, which doesn't cover much of any rodent, let alone larger animal region in the brain. In order to help solve that problem, I undertook to spend my group's money at Genelia to build a next generation of probes advancing the state of the lithography. These are still available commercially. You can buy them. They're licensed to Cambridge Neurotech. They increase the lithography resolution from 2 microns to half a micron, so you can get 4 times as many channels on a shank. But you've run out of room if you don't have better lithography. And so if you want more coverage or denser, which is the problem with these devices, you need to have better fabrication technology. The reason I went to IMEC was not because I thought they were going to be my solution, is that they were a center for this thing called the EU Neuroprobes project, which, unlike the typo on this file, says from 2027, it was 2007 to 2011. I went there in 2010 as the project was wrapping up. They had built a switchable shank probe. They were unfortunately quite thick. They had 250 sites per shank, but they only had 8 activatable, so you could drive your 8 around, but it didn't solve the problem of how to get tissue coverage on a shank. It is not an improvement over, the shank coverage of that Buzaki 32. And then this very clever idea to make, a bed of nails out of shanks turned out to be not manufacturable. And so these probes were never distributed. And so the solution is still better lithography for shank traces, is that I was at 1 micron pitch, half micron lines and spaces. Even passably good state-of-the-art lithography at the time could do half micron pitch, so twice as many. The really big difference is that conventional technology that you can access in a university clean room has 1 layer of 1 micron pitch. You can get 6 layers of 1 micron pitch in the technology that of half micron pitch, and the technology that IMEC was able to practice. On top of that, there's an interconnect problem. You got to get wires out to amplifiers, and so the way to solve that problem is simply to build the amplifiers into the integrated circuit. So there is no interconnect problem. It's solved by this same high resolution lithography. And so this is a picture that Carolina gave me long ago. I would like someday to get a better picture, but it illustrates the issue, is that this is a previous generation NeuroPixels-like device. You can see there are 6 layers of metal listed. The connections between the layers are on these side places. And I drew a line here of about 10 microns as best I could with this tilted point of view. And you can see there are about 22 traces in a 10 micron patch. And so, a factor of 2 plus better than I can do, and multi-layer. And so you just get more capacity on a shank because you got, more wires coming up the shank. So, using that technology, we made the first generation Neuropixels probes. They had in their final embodiment 960 sites with a pattern like is shown on the bottom. They were 23 microns thick and 70 microns wide. That decision was made to maximize the channel count. IMAC offered me 180 with a 50 micron wide shank or 384 with a 70 micron wide shank. So we tested the stability of those in rats and opted for 70. And then there's a flex out and a head stage. All that together weighs a little over a gram. And so these were introduced on a limited basis to the funder networks in 2015 and to the wider world in 2017. I like to show this slide because what I say is that the first thing we had to do is find someone who could make it that would make it. There are dozens of factories in the world that could make this. Only one of them, as far as I know, would be willing to do it, and that was IMAC in Leuven, Belgium. And then I had to find someone to pay for it. The initial estimate was 4.2 million euros, which at the time was about $5.5 million. And this consortium of funders agreed to bankroll that, the welcome through a grant, primary author by John O'Keefe at UCL. And so many of you, if not most of you, have seen these systems. There's a 5-meter cable. There's a picture of the head stage. Carolina showed what the probes look like on the wafer. I showed this picture. It's a bit out of date. That IMAC has shipped more than 13,000 probes to well more than 1,000 labs. They're sold at cost. That is 1,200 euros for Neuropixels 1, 1,500 euros for Neuropixel 2. At least that's the 4-shank version. Support is not through the vendor because they don't have any way to pay for it. Jennifer and Bill have been the primary support. The community has been a great support through the Slack channel. So if you haven't signed up for the Slack channel, you should. The other important people on this slide are these two people who are HHMI lawyers, Heidi Henning, who wrote the contract for the first Neuropixels probe. It took a year to get all of those parties in that previous slide to agree, and Chris Heiberger wrote the contract for Neuropixels 2. You might have thought that would be faster. It still took 9 months. Without that legal support, there would be no Neuropixels. This is the surprise. We thought we were making probes for rodents. It turns out we were making probes for all kinds of animals. Who would have thought that, nearly 20% of the use cases would have been cephalopods. And I assume this list is out of date and will continue to grow. So this is the business end of things. There were 2 site patterns, the initial one on Neuropixels 1. Then a second site pattern was chosen, actually with Neuropixels 1, to test drift correction. I don't think we ever did this really quantitatively, but nonetheless, in the end, we chose that this has more information leverage for spike sorting, but it's harder to correct for drift. By far, the dominant use of these devices is in acute head-fixed recordings, and so the brain is still relaxing relative to the probe. I mean, the probe is attached to the building, and the mouse's brain is not. And so you see relative motion during recording, and that turns out to be among the most difficult problems to fix. It's less of a problem in chronic things, but the site pattern remains. The new site pattern, I think I'll show in a bit. These are 20 micron pitch. We call these rows. The 2.0 and the NXT site pattern is at 15 micron pitch. There's only 3 micron gaps. So if the brain moves a little bit, you cannot lose a neuron. The recording system initially was, I'm not going to talk about one box. It was initially PXI chassis. This is a very widespread industrial, very high-speed bus system used all over the world. IMEC made a controller that fit into the PXI chassis. You can buy almost any other functionality you want in a PXI chassis, and it can connect directly to the PCI bus in a high-speed workstation, so you never run out of bandwidth. This is the inside of a Neuropixel 1 probe. Carolina showed you the inside of an NXT probe. The differences here were that you have adjustable amplifiers, and so every pixel has a switch under it. the pixels to answer that question. Neuropixels was a term suggested by IMEC. I think our initial project manager, Silke Musa, had a significant amount to do with it, but I wasn't told exactly who made the first suggestion. The notion is it's a bit like a camera for electrophysiology, and that's why each element of the array is a pixel. So every output line, 384 of them, goes to a preamplifier with a gain of 50. That's not adjustable. You can adjust the references to be external or internal. And then in order to have a smaller A to D converter, 10 bits in this case, the signal was split between high speed and low speed. There are 24 or 32 in this case. I can't remember which. I think 24. Multiplexers and A to D converters. You always multiplex analog because A to D converters take a lot of wafer real estate. And as you can see, the base was 6 by 9 millimeters. We took very few chances for this project because we knew at a price tag of $5.5 million, if we didn't make one work, we were going to never get another nickel. And so this is essentially a cut and paste design of elements that had been used elsewhere in other projects. The one novelty was the site material. Everyone in the world was using gold or electroplated PDOT. You can't electroplate through neuropixels. And so Silke has the project manager has a single inventor patent of porous titanium nitride, which has turned out to be a fantastically robust and useful site material. It is the same site material used on every generation of neuropixels. So this is what happened in November of 2017. Nature published the first paper. Matteo insisted that I resubmit it to Nature as opposed to Nature Neuroscience, and they were kind enough to review it and publish it. Then, you have to ask the question, so why not just declare success and stop? And the answer is because NeuroPixel 1, while it's small enough to fit on a mouse, is pretty big and clunky for a mouse. And all of the sites lying along a line, and we wanted a multi-shank probe from the beginning, but we needed another €1,000,000, and we thought we better prove that we could do something before. And so another proposal was written to Wellcome Trust, this time by Matteo. But since Matteo wanted to include Opto, which you'll hear about later today, in that proposal, we didn't have enough money to pay the €1.75 million we needed for 2.0. And so we very quickly, less than a week, rounded up some others. Genelia made their contribution, the Sampolamode NERF in Leuven and the Kavli in Trondheim all paid about a fourth of the remaining €1,000,000 bill, and off came NeuroPixels 2. This is an antiquated picture of NeuroPixel 2. You will see a better one later. The most recent probe now is 4 NeuroPixels 2 into a single chip. The first 1536 channel probe that the project just produced, they were just released last month. You can buy them. They're not cheap. They take a lot of wafer real estate. They have 4 shanks. Each shank has its own base. And so you can program each shank with its own 384 channels, but you can't move them around between shanks. There is a head stage that takes 2 probes, and you can plug that all into one box. It's the same fabrication technology. It's just a 2.0 probe, not segmented, readdressed. This was a really high impact problem that when I was traveling around talking to people about neuropixels, primate scientists asked me, why are rats getting all the help? And I said, because I work at Genelia and we don't do primates. And so Krishna Shenoy and Tiran Moore, these guys, helped me organize a workshop at Genelia. We designed this probe at that workshop. I went to HHMI headquarters and they were generous enough to write the €1,000,000 check to make this device. These are now revolutionizing primate research. I think they are the biggest change in electrophysiology and animals. Rodents had okay probes. Monkeys did not have very good probes, and so this is a really big step forward, as is evidenced by my friends from Columbia is saying, before we used these, a good day was 20 units. They always put in 3 at a time. Now a bad day is less than 1,000 units, a 50x improvement in monkey productivity. This is a really big help to the system. Here is the whole family one, which will be ending within the next 12 months because you're going to substitute for it instead Neuropixels 2.1 shank. There is the NHP probe. There was an ultra-high density probe. You may buy this. It was made in order to ask some fundamental questions about spike sorting and neuronal identification from waveforms alone. Opto, you're going to hear about later in the day. Quad base, I just told you about, and NXT, Carolina told you some details. I will add just a few right now. So this is what NXT 3.0 looks like. That is the devices we have in my lab at Johns Hopkins right now. It's also a 1536 channel probe, but you can put as many as 912 channels on one shank. You still only have 1536. We will get a 2-probe head stage about the end of the year. There will be a new controller, a new head stage, and a new cable. There is virtually no cross compatibility between NXT and 2.0, which will be the alternative generation. No one-box compatibility as far as I know. These are successfully now implanted in mice at Johns Hopkins. In my lab, we are getting, about 1,100 kilosort good single units and another 1,400 kilosort multi-units from one probe. And we think 4 probes are perfectly plausible. A routine experiment in my lab now is 4 2.0 probes. These are more or less the same size. So we are anticipating in the not very distant future 6,000 channel mice freely moving. In the future, there will be a pre-production release of NXT 2.3.0. I would guess about the middle of 2026. That's not final yet. IMEC does this for every generation of Neuropixels. They sell them at a premium price in large groups from the research organization to practice making them to increase the yield and drive down the price. The final version of the recording system, which will not come out until 2027, will have a smaller head stage of the order of the size of 2.0. So that since we are using 2.0 head stages on mice now, I assume that we will be able to use 2.0 head stages on NXT probes, again, to make 6,000 channel mice routine. Neuropixels Opto, which is not out widely yet, you'll hear about later. I would like to make a probe for electrical stim and record. I haven't found anybody yet's willing to pay for it, but the primate community insists they need it. And I'm not going to talk about it, but a stereo EEG probe with single unit capacity would be a transformational development for human electrophysiology. Thank you.